I want to, before we get started, new module starting today.
What?
What?
Sorry,
Oh, okay. We're going to start equilibrium today. All right. We'll spend hopefully 3 or 4 lectures on equilibrium. And then I'll spend the rest of the time on my favorite topic of the semester, which is kinetics. Right? And we're going to find that they're both one module together, and there's a good reason. We'll see equilibrium and kinetics are actually intimately related to each other. So slightly different perspectives on the same question. But I think it's better to start with equilibrium and move into kinetics instead of the other way around. And I think that'll become clear in the next day or so, next couple lectures. What I want to do first is give you a slight discussion for about 10 minutes on the current homework, problem 3 on the current homework. I realized that, let me just put it this way. Problem 3 is pretty straightforward, but you just need a little bit of conceptual push to get it started. Okay, and it's a big Excel question, some plotting and stuff. I just want to talk about how to analyze the problem, get you kind of started, just to give you something to think about, so that when you go to LA sessions or office hours or go work on your own, that you kind of know where to start. Okay, so I'm not gonna bring up the homework. I'm just going to start talking about it. I'll just assume that you can look at the homework yourself. We'll just talk a little bit about. Actually, let me go ahead and pull it up while I'm sitting here. Problem 3. We're looking at problem 3. All right, which is about the vaporization of methanol. All right. Now I'm going to write methanol, MEOH, like an organic chemist. Let me pull up the problem. So I just want to talk very briefly about the 3 parts. All right, and just talk a little bit about what you need to do. Okay, so let's look at 3.1 really quickly. 3.1 is on the vapor pressure of methanol. I'll give you a nice formula. I'll copy and paste it over. That explains what, that gives you the exact value of the vapor pressure of methanol as a function of temperature along its coexistence curve. All right, so I get this formula here. All right, a couple things I want you just to note is that this formula is a function of this x variable, and x here is defined as T, the temperature, divided by the critical temperature. And I give you the critical temperature for methanol. It's 512.60 Kelvin. All right, so this equation is unitless because the variable has no units, and Kelvins divide out. Right? And that makes sense because the left-hand side of this is a logarithm. Logarithms don't have units. Okay, so this is unitless. So something to keep in mind. So what you can do is you can plug in some percentage of TC, fraction of TC, right? Somewhere between 0.1 and 1, something like that, and you get the pressure out of the vapor pressure. So the output of this is the vapor pressure of methanol. And the most important thing I want you to note is that this is a logarithm. This is the vapor pressure. So this is the log of the vapor pressure as a function of temperature. All right, so in order to get P, right, if you want to get the vapor pressure at a function, an x, temperature x, you need to take e to the ln P. Right? You need to take ln e to this equation. All right, so just remember that. This is the logarithms. And you'll understand why it's logarithmic because you'll see at low temperatures, like say 100 Kelvin, kind of near the triple point of methanol, that the vapor pressure of methanol is basically non-existent. Right? It spans multiple, like 12 orders of magnitude. Okay, so it's useful to use logs here because the value varies a lot. Okay, so that's a really easy question, and what it asks you to do is to show that the boiling point at 1 bar is 337.67 Kelvin. All right, and I just want to give you, I'm surprised I haven't mentioned this yet. I'm really sorry about that, but I want to give you a really, really simple concept about boiling. I maybe have mentioned this in passing, but I didn't really formalize it. What does it mean for something to be boiling? All right, boiling occurs when the vapor pressure is equal to the external pressure, the atmospheric pressure. Okay, so that means at 1 bar, boiling occurs at when PVAP is 1 bar. All right, so you just need to figure out what X value gives you 1 bar of vapor pressure, and that'll be the temperature, right? And you'll see that it's that temperature. Okay. Just a quick check. All right, that's a good thing to remember. This is always true, right? The boiling always occurs where the vapor pressure is the external pressure of the system. Okay. All right, so that's a really easy problem, not too hard. Just a little plotting in Excel. Let me go to 3.2 now. 3.2 is another plotting problem. It's just plotting. It's got 2 equations. Here you're going to plot and calculate the densities of liquid MEOH and gaseous vapor methanol. All right, I give you 2 equations for each of them. Right, this liquid one is, this density is called, I call it P sub L for the density of the liquid, and this one is P sub G, which is the density of the gas. All right, it's just a plotting problem. I ask you to plot a couple things, so you just basically make a table of values for different temperatures, and I'll show you what the formulas look like really quickly, just to remind you. So here's one of them for the liquid formula, the liquid density. And just as a pinpoint, again, X here is exactly the same thing, right? So you'll use the same X variables for all of these problems. They're all relative to X, right, which is T over Tc. So you can just basically have a list of temperatures, and you can just plug in equations for those temperatures for all the problems. Right, you'll see that this is a function of P sub L over P sub C minus 1. So you got to move this minus 1 over here and multiply by the density of the critical fluid, which is P sub C. I give you that value in the problem. This is a number. Oh, you can't see that, can you? Bless you. This is just a number in the problem. So anyway, just a simple plug and chug question in Excel. I just want to show you the gas one because I know someone's going to not notice this. I know it's just one of those things that sometimes people just don't see. Is that for the gas one in particular is the logarithm of this ratio. This is a log. All right, so the liquid density is a linear function. Well, it's not linear, but it's not a log. And the gas is a logarithm instead. All right, so you have to remember that. You have to take e to the value. And the reason why is, of course, the density of the gas varies wildly. Right? Depends on the temperature. Right? Low temperature, the gas is very dense. At high temperature, gas is very dilute. Right? It's not dense at all. Everything's spread out. So just make sure to remember that there's a log there. Okay, simple problem. Just again, just plotting. 3.3 is the tricky problem. So 3.3 asked to calculate the enthalpy of vaporization at all temperatures in the range of 3.1 and 3.2. Okay, so what it turns out is that 3.1, all the answers, all the calculations that you do in 3.1 and 3.2 are used in 3.3. Okay, you can, when you have the densities and you have the vapor pressure, densities of both phases, and you have the vapor pressure, you can calculate the enthalpy. Now let me show you how you do that. So how do you do this? Right. So we apply the Clapeyron equation, right, which says that dP dt, this is the vapor pressure of the system, is equal to the enthalpy of vaporization divided by the temperature times the change in the molar volumes. Okay, so that means therefore that you can always calculate the enthalpy of vaporization if you know the derivative of the vapor pressure with respect to temperature at a given temperature times T, the temperature that you're measuring it at, times the change in the volumes. Okay. So what we need to do is figure out how to calculate. T is easy, right? That's related to x. Right, so you have that. That's just an input variable. We have to figure out how to calculate this and this, these two terms. So let's do that. Right? Delta v is really easy, right? Because delta v, for delta v, is equal to 1 over the molar densities. Right? So that's going to be 1 over the density of the gas minus 1 over the density of the liquid. Okay, so if you, from 3.2, you've already calculated these two numbers. You'll have a table of them in Excel, column of densities for each material. So all you have to do to calculate delta V is just take 1 over each of them and calculate the difference. Really easy. Right? Just take make a new column that's 1 over the density of the gas and subtract it off 1 over the density of the liquid. All right, so super easy. This all come from 3.2. Right, and now we have to figure out how to calculate the slope, dp vap dt. Well, remember that we have in 3.1 a formula for the vapor pressure. Right? You can calculate the vapor pressure at any temperature. So we just have to now calculate, but we unfortunately we have the log of the vapor pressure, right? But 3.1 gives the log of the vapor pressure. Okay, so we need to figure out how to take a derivative, how to get dp dt from ln of p. All right, and the idea is just use the chain rule. All right, so if you take the derivative of that function for the log of p from 3.1, right, this is the 3.1 equation, and take a derivative of it with respect to temperature. You take that equation and just, it's very easy derivative, right? It's just like a polynomial. It's got an x squared, x to the third. Really easy calculus. You do it in your head. So how would you get, right? We need to get rid of this log somehow. All right, so we just apply the chain rule, right? The derivative of the log of something is 1 over that thing. So we get a 1 over p, the vapor pressure at that point, times the derivative of the interior of the log, which is dp vap dt. Okay, so that means that we just do a little bit of algebra here. This means that dp dt, the slope of the vapor pressure with respect to temperature, is the derivative of the logarithm function, which you have from 3.1 with respect to temperature, times the vapor pressure at that point. Yeah, that's it. Right, so that means, therefore, that delta vap of H is going to be equal to, let's just plug it all in. First, it's going to be the derivative of the log of P. That's the function from 3.1 dt, evaluated at the temperature that you want to measure it at, times the pressure at that temperature, times the temperature, times 1 over the densities differences. Okay, so what you'll do, this value comes from 3.1, right? 3.1, you calculate all the vapor pressures for all the temperatures. This is the temperature. You got that one, that's your x-axis basically. You got these from 3.2. So all you have to do now is just calculate the value of the derivative of the 3.1 equation with respect to temperature at each point. So this comes from the derivative of 3.1. This is d by dt of 3.1. This is the 3.1 output. This is the 3.1 input. And this is the 3.2 output. All right. There's just one correction we need to make. I'm just going to add one more thing here. Is that I've done all this with respect to t, but our formula is with respect to x. So we need to do the chain rule between t and x. Really, really simple. All you do, all that means now is that you replace this with x, and you replace the t with x. Okay. So You just need to calculate the derivative with respect to x of the formula from 3.1, calculate all its values at different values of x, the vapor pressures at those values of x, the value of x, and then the difference of the densities at that value of x. All right, so you'll have a big, long list of temperatures, right, from, like, say, 100 Kelvin to whatever the critical point is, 500 Kelvin. You'll have a column for the vapor pressures, a column for the temperatures, of course, a column for the densities of the gas, a column for the densities of the liquid, and you'll calculate the derivative of the function, then calculate the derivative at every x point. That'll be another column, and then you just take a product of those columns. The one note that I want you to make is that we want the units, right? The unit should be joules per mole, and that means that pressure has to be in pascals. And what am I missing? Temperature in Kelvin. Oh, and volumes in cubic meters. Okay. You can do conversions if you. The problem gives it to you in liters and bar. All the data is in liters and bar. So you can just convert all of the things to pascals and meters cubed if you want, or you can just do all your conversions and just do it in terms of pascals or in bars and liters, however you want to do it. But my recommendation is really easy, just to have a list of pressures in bar, and then create a new column where it converts all of them to pascals. You have all your volumes, you can convert them to meters cubed. Just makes it easier to do it that way. All right, so just make sure you do this, and everything will work out just fine. Any questions about that? Yes, ma'am.
So for the, like, when you're saying from 3.1 doing the derivative, in 3.1, didn't you, I mean, I haven't done the problem, so like,
yeah.
But
don't you
not calculate the derivative though? Like in that, because you're only, am I wrong?
All you have to do is just take the derivative of this function, right? So it's going to be plus 10.75 over x squared. That goes away, minus 3.6.
Okay.
You get it? This will be 2x, this will be 3x squared, and this will be 1.7 times 1 minus x to the 0.7.
Okay.
Right. So just take a basic derivative of the function, and then create a new column that calculates that function for every temperature.
And so why are you able to do, like, when you substituted for t, you just put x, why are you able to do that?
Chain rule. Very simple. I'll just do it on the side here. Right, what we really want to calculate is dp dx, right? Oh, sorry, we want to calculate dp dt, but our function's in terms of x, right? So how would you calculate that? You calculate the derivative of p with respect to x, and then the derivative of x with respect to t. X is equal to t over tc, and dx over dt is 1 over tc. And so you get a factor of 1 over tc on the outside of your equation, and that's just x. I'm just using the chain rule.
Thank you.
Yeah. So just convert all your t's to x's, and you'll be okay. So just don't use raw temperature, just use x instead everywhere, and you'll be fine. It just froze. Why is it freezing? Okay. Hello. Let me stop my share and try again real quick. Is it this computer that's frozen? Hello? Why am I dying? Oh, Zoom just crashed on me. I'm sorry, guys. All right, here we go. Okay, very good. All right. So I'll save this. It's on my recording, and I will also save it to my notes for today, so you can just look it up if you have any questions. And of course, the ladies in the CLR are well aware of what you need to do, and of course, I'm always happy to help you in my lecture or my class as well, or my office hours. All right. I just want to make a, yeah, that's fine. Yeah, I don't have any more notes to make about that. Okay, let's continue on. All right, new topic today. All right, today we're going to start talking about chemical equilibrium. Oh, sorry, let me make this full screen. All right, we're going to kind of slowly work our way into the chemical equilibrium because we need to relate the concept of chemical equilibrium to kind of our box parameters that we've been talking about all this time. All right, so let's think now what we're going to do is we're going to have, let me think how about my notes does this. Yeah, so let's think, for instance, right, we want to use, the idea here is to use a chemical box. And what do I mean by a chemical box? It's one that's defined by dG, by the Gibbs free energy. There's an SDT, all right, plus PdV, plus the sum over all the chemical components of their chemical potentials times the change in their moles. All right, so this box, if you will, has some molecules in it. We don't know what kind. Maybe there's some yellow ones, and some purple ones, some green ones, some red ones, and some orange ones. They're different molecules. And this box is defined by the temperature, the volume, and the mole numbers, if you will, of each of these materials. Right? So we have N1, N2, N3, N4, and N5. All right, so we're going to track all the different moles of our different components. And I want to talk in particular, right, so we want to think about equilibrium, right? When we think about equilibrium, we're thinking about products and reactants, right? We're thinking about molecules that are, say, molecules 1 converted into molecules 2 and vice versa, right? You have exchange of material, chemical exchange of material. Right, so N1 maybe can convert to N2. Maybe it's N1 plus N2 goes to N3 plus N4. Right, you have some equilibrium of products and reactants. Right, and we're going to do this. Right, we want to do this at equilibrium. And how do we do chemistry? Well, we certainly don't. When we want to do chemistry, we don't want to change the volume of our box or our temperature, right? So in a chemical reaction, right, we're going to fix the temperature. We fix T, and we fix V, right? Because you have to have a flask, right? Right? And what we're going to do is, right, we're going to set this box up with our different materials, right? We initially sprinkle in a little molecule 1, a little bit of molecule 2, molecule 3, molecule 4, molecule 5 in the box. Right? We have all of them kind of coexisting at the same time. And we're just going to let the system equilibrate. Right? And so that means, again, the temperature, right? If you bring in some hot N4 and some cold N1, they might exchange heat and entropy, temperature together, right? They might exchange entropy. The pressures may change, the partial pressures of each of the materials may change. But by and large, we're just going to let everything equilibrate. Right? We're going to take this box, we're just going to let it go home overnight, come back in the morning, and see what happens. All right, so we're going to let this equilibrate. And what does it mean to equilibrate? Well, it means that we're going to let the system equilibrate at the temperature and the volume, which means we're going to try to find, the system's going to find the lowest, sorry. What does that mean? It means that the system is going to find the arrangement of the atoms and the molecules and all the variables such that the energy is minimum, right? We want energy to be as negative as possible. Right? So we want to find, right, this system is going to adapt and it's going to move around until the point where dG is equal to 0. Right? And the idea, again, is that imagine that we have this surface, right, where I put G here. And let's say it's a two-component system, N1 and N2, and I want to plot G as a function of those two variables. Right, so maybe G kind of looks like a little surface that looks like this. Let's see if I can draw this. And maybe, for instance, the surface kind of bends down like this, out here. Maybe it goes up like this. Right? We have some three-dimensional surface. And there's this minimum point right here at the minimum energy, right? This is a minimum. As a function of N1 and N2, right? And the system's going to sit there, right? So imagine that we start to sprinkle in some other value of N1 and N2, right? Maybe we start up here. We have a lot of N1 and not a lot of N2, right? So maybe we're up here initially, right? So we sprinkle initially up here, right? So we have some mixture of N1 and N2 up here. And what's going to happen is the system is going to equilibrate. N1 and N2 are going to interconvert between each other or exchange, whatever they're going to do to lower the energy, right? So the system is going to traverse the surface and exchange N1 and N2 until we reach the minimum, right? So there's going to be, there's some point here, G, we'll call it G min, of N1 and N2, that is the equilibrium point. This is the equilibrium point. Okay. And so what the point of chemical equilibrium is to track this, right? We start with a box of some mixture of molecules, and we want to know where is it going to end up after we wait a while. Or, for instance, we just have N1 and N2. Imagine we put 2 moles of N1 and 1 mole of N2. Is N1 going to increase in a material and N2 is going to come down? Or is it going to go the other way? Right? And N1 converts into N2. Right? So we want to think about that, right? How does the system equilibrate across its components? This is a very different question than we talked before. We've been talking for the last time about these two terms, right? About the energy change, right? The enthalpy, the entropy, the work that a system does when it equilibrates. But in this system, right, we fix T and we fix V. Right? So these terms go away. Right? So in this chemical system that we're looking at, dG is only a function of the chemical potentials. Right? And at equilibrium, this is equal to 0, right? Because dG is 0. Right? So depending on our materials, the amount of materials we have, the system is going to, right? Temperature and volume are fixed. Right? The system is going to exchange molecule 1 with molecule 2, 3, and 4, move them around until it reaches this minimum that's only a function of the mole numbers. Right? This is a product, this is a function, or thermodynamic function is only dependent on the mole numbers. Right? So the idea is that we need to figure out the right distribution of our molecules such that we hit this minimum. Right? This is chemical equilibrium at its very basic. All right? So again, when you guys think about chemical equilibrium, you're probably thinking like, okay, I've got this coefficient that's like the concentrations of the products divided by the concentrations of the reactants. Right? We'll get there. Right? That equation for the equilibrium constant, KEQ, as you might remember, comes from this expression. Right? We're going to take this idea of the chemical potential and translate it into the chemical equilibrium constant that you know and love, or fear. I don't know how you guys feel about equilibrium. I fear it a little bit. We're gonna try to unpack this equation a little bit. What is the chemical potential, and how does it? Right, if you think about it, right, these are only going, D and I, these are just the change in the mole numbers, right? They're going to go up, they're going to go down. But the chemical potential tells you kind of how much one is going to go up versus the other one going to go down. Right? It's going to tell you something about the distribution of energy and how removing one changes the energy as you add another one. All right, so let's talk a little bit about chemical potential today. All right, let's get a sense of what this number is, right? And it should be important, right? Because certainly, if we look at the Gibbs energy, right, these are our extensive parameters of our equation. Right? Our extensive parameters of our system are entropy, pressure, and chemical potential, right? Entropy and pressure, of course, are extremely, extremely important. Right? They define so much about our system. So this chemical potential must be equally important for our system because it's weighted equally to the entropy and the pressure. Right? So there must be something important energetically here that we need to look at. Right, so let's talk a little bit about chemical potential. What we're going to find is that chemical potential is just a fancy way to say each material has its own Gibbs energy of formation. Right? What we're going to find is that the chemical potentials are just the Gibbs energies of formations of each molecule. Okay? The idea is that each molecule brings to the table some heat, some stability. Right? They have some energy, internal energy to themselves. The Gibbs free energy of just the molecule by itself. And each one has its own Gibbs energy. And the chemical potentials track how the total energy of the system is distributed amongst those separate molecules. All right, so we're going to see that if we can calculate the Gibbs energy of formation, which we can do, we've been doing that for a while now, right? You calculate the enthalpies and the entropies for each molecule in your system. The chemical potential is just that Gibbs energy for that molecule. We'll see that in a second. And that should be clear from the units that chemical potential has something to do with energy, because the units here, of course, are kilojoules per mole, right? And the units of this are per mole, or sorry, just mole. Right. Sorry, let me just change this to kilojoules. Sorry, this is kilojoules, and this is mole. So this must mean that mu sub I has units of kilojoules per mole, right? So chemical potential has energy. It's an energy, some sort of energy. And in fact, it's a potential energy. It's energy stored within each of the molecules, right? Remember, the idea is that you want the entire system to be at as low of energy as possible. So if you have a bunch of high energy molecules in your mixture, it's probably likely that those are going to disappear for lower energy choices in order to bring the energy down. Tells you something about the relative stability of each of the molecules in your mixture. All right, so let's look at that a little more carefully today. Okay. Any questions so far? Okay, so let's talk chemical potential. All right. So the chemical potential, I'll call it the chem pot, is a molecule-specific energy, or molecule or component, because sometimes you might have atoms, specific energy. That only has meaning in systems with multiple components. Right? The reason why that is, if you can kind of think about it, you have a box with, you have one single box of flask. If you have just one molecule in there and it doesn't do anything, then who cares about the chemical potential of that molecule? It's never changing. Right? You're never losing molecules if you have a closed box with a molecule that doesn't react or do anything. Just one pure component. We don't have to worry about the chemical potential, right? Because it's just one component. It doesn't change. So this is something that tells you something about the relationship or the balance of energy between multiple components. One of the things that you're going to see in problem 1 of the homework, which talks about the chemical potential, is that you may define the components as different spaces. For instance, imagine you have, in problem set 1, you have a box that's compartmentalized into two sections. In the left side section, the first section is filled with molecules, and the other one on the right side does not have molecules. And you can show with the chemical potential, this is what problem set 1's about, that there will be a flow, a diffusion of molecules from the left box to the right box to fill the space. Right? You can use chemical potential, basically at the chemical potential of the left side, the chemical potential of the right side, which tells you something about how the molecules are flowing from left to right. So you use it in that context, where the components are different spaces. For instance, that's how you calculate about diffusion. Right? You have a gas or material that has a higher concentration on one side of a membrane, and you have a low concentration on the other side. Entropy will tell you that the chemical potential is driving that system to mix and flow molecules from the outside the membrane into the membrane, right? Like a sodium gradient in outside of a cell wall, right? Like a cell membrane. So osmosis, diffusion, things like that. These are things that can be related to chemical potential because the components are spaces where one molecule is flowing from one space to another. Okay. We're not really going to talk about that here in terms of equilibrium. Here we have a single flask with a molecule that can exist in different states. So, a chemical system that can be different types, right? Products and reactants. So it's always defined relative to multiple spaces, multiple parameters, multiple components. All right, and it's a number, right? It's an energy. And the idea is, so just some simple observations. Right. The first thing we'll look at is that for a two-component system, at equilibrium, the chemical potential of the first one times the change in the moles of the first one is equal and opposite to the chemical potential times the change in the moles of the other one. That should make a lot of sense, right? Every change that you make, if you only have two choices and it's an equilibrium, if you make one go up, the other one has to go down. All right, so let's kind of look at, for instance, right, what does this ratio tell us, right? Right, it says something that, for instance, that the change in the ratio of the changes of the molecules in a process, let me make sure I got the math, is equal to the inverse ratio of the chemical potentials. Right? So for instance, imagine that you put 1 mole, let's say you have a system that just has 1 mole of component 1 in it initially, okay? And you go let it overnight, and what you come out and find is that at the end you only have 0.25 moles of that molecule. Okay? So that means that dN2 is 0.75, dN1 is 0.75. Oh, sorry. So let's start over again. So let me just write it down so I don't get confused. So let's just do a simple example. Let's say initially 1 mole of number 1 and 0 mole of number 2. And then after overnight, 0.25 mole of number 1 and 0.75 mole of number 2. Right? So what would that ratio be? Well, dN2 is 0.75 and dN1 is 0.75. Right? And so this says, oh wait, that doesn't make any sense. Hold on, what am I doing wrong here?
The number of moles of 1 is 0.25.
Oh, sorry, thank you. That's right, I'm sorry. Yeah, that's right, thank you. I know what I'm doing wrong, right? So this is 1/4. And I have a negative sign too here, right? Because you gain.
Yeah, but isn't dN?
It's the other way around. Sorry, yeah.
No, I mean like.
But it's still the change.
Yeah, so that confused me.
Right. So dN2 increases by 0.75. Yeah. Okay. So that's a bad example. I'm sorry, guys.
That's okay.
All right. So we'll come back to that. I'm sorry. Chemical potential is a little tricky, right? So you can imagine that maybe, for instance, the system exchanges, like say 1 mole of 1 for 2 moles of the other. Right? You lose 1 mole of 1 and you gain 2 moles of 2, right? That would be a ratio of 2, and that says that the chemical potentials are related by a factor of 2 as well. All right, so what we're going to find is that what that means is that, for instance, if the system wants to make more 2 than 1, it should make a lot of sense that, right, if dN2 is larger than dN1, right, that's going to mean that the chemical potential of 1 is larger than the chemical potential of 2. Right? And the idea is that the system has more energetic impetus, that's maybe a complicated word, energetic benefit to remove 1 to make 2. Right? It prefers to make 2 because 2, in some ways, as we'll see, is more stable than molecule 1. And so naturally, the system wants to go to something as stable as possible. So the chemical potentials tell you a little bit about how that tracks. If you have 2 molecules that are basically the same, and that you roughly get a 50-50 mixture at the end, they just equilibrate out, then their chemical potentials are basically the same. Right? There's no preference for the system to be in 1 or 2. So when it goes to random, when it randomizes and equilibrates, you get 50-50. And so the chemical potentials are precisely the same.
I have a question.
Yes, go ahead.
So like when you're saying though it being 50-50, like I don't see how that necessarily like is proven by that, because I thought like, because it's saying the change, right, in N2 and change in N1. So wouldn't like the only way that you would get a different change be if you needed like, let's say like 2 moles of 1 to make 2? So it would just tell you about like
the stoichiometric coefficients.
That's what it would tell you.
Yes, it would tell you something about stoichiometric coefficients as well. We haven't introduced those yet, but you're exactly right.
Okay.
You're exactly right. No, I'm thinking of a system. Where you have an equilibrium between A and B, 1 to 1 mole, but equilibrium is product favored. So you end up making, okay, so let's say it's not product favored. Equilibrium is equal, so you get K equals 1, right? So you have equal amounts of product and reactant. That means the chemical potentials of the 2 materials are the same. Now imagine that you put in molecule A and you let it equilibrate, and you lose almost all of molecule A, and you gain almost completely molecule B, and tons of molecule B. You end up finding out that the chemical potentials are different than each other. Maybe it's not that clear from this expression.
Well, I just mean like, because like if you change, like kind of like the example you were saying, like you both would change by 0.75.
Right, I understand what you're saying.
Okay.
Yeah, I understand what you're saying.
I'll wait.
Yeah, let's wait. Let's wait. We'll come back to that, all right? Because we haven't introduced stoichiometric coefficients yet. What I want to get from this, all right, this discussion, is really just kind of a general idea. Right? The idea is that we need to think about the relative magnitude of the two potentials. Right? So the idea is that if mu1 is greater than mu2, this means that the system prefers. Oh, I know what's wrong. We'll come. Let's just ignore the last things I said for about 10 minutes, or for the last 5 minutes. Okay, we'll come back to that. I know my issue. All right. So let's just say we go and measure our system at any point, and if we measure the chemical potential of 1 is greater than 2, this means the system prefers to convert 1 into 2. All right. There's a benefit. Right? And if U2 is greater than mu1, the opposite is true. All right, and this is my problem, is that if mu1 is equal to mu2, this means the system is at equilibrium. It has no preference one way or the other. All right, so naturally, Monica's confusion was, it seems like we always get that mu1 is equal to mu2 at equilibrium. Well, that's exactly correct. Because at equilibrium, there's no impetus for one to go over the other. Right? If A goes to B as much as B goes to A, they're both equally likely. So at equilibrium, mu1 is equal to mu2. So the idea is that we actually want to track where equilibrium is. Right? So let's say we start our experiment up here on this point on this surface, right? And up here we're going to see, right, it's not equilibrium, we're going to see that the system wants to take whatever value of N1 and N2 are here. We're going to want to see that this system wants to convert some of N1 into N2, right? So there's going to be a difference at this point. Let's say, for instance, that at this point, that mu1 is greater than mu2, right? And so what does that mean? That means that this system, in order to lose energy, right, it has to lose some molecule 1 for number 2. Right? So we know that what the trajectory of equilibrium is going to be if we stop it at this point and measure the chemical potentials. and mu1 is greater than mu2, then the system is going, we know it's going to start losing 1 and making 2 as it goes down this potential to the minimum. Right? Meanwhile, we could be on the other side. Right? For instance, imagine we're over here, right? And at this point, mu2 is greater than mu1, right? And that means that the system wants to lose 2 and make 1. Right? So the chemical potentials at any point along our reaction will tell us something about the direction the reaction is going to go. Right? Gives you some directionality. Right? So if we can measure these potentials in lab, which we can do, I'll show you an example in just a second, we can watch the system. We know, so if mu1 is greater than mu2, we know that we're going to lose some of molecule 1 as we wait to convert to molecule 2. Right? This is just, I mean, again, just think about equilibrium, right? You start with a lot of moles of reactants, right? You fill a huge excess of reactants, you're going to lose a bunch of them. And equilibrium to form products, maybe you don't form a ton of products, maybe you form a ton, it all converts to products, maybe only partially, right? That's going to have something to do with where delta G, where equilibrium occurs. The value of N1 and N2 that give you G, the equilibrium point, right? That's going to depend on the reaction. But the chemical potentials tell you something about the direction the process is going. Right? So they give you some directionality. Right, so what does that mean then? Right, so chemical potential that's a bad color, tells you something about the future status of your chemical system. If mu1 is greater than mu2, you know you're going to lose some 1 to form 2. mu2 is greater than mu1, you're going to lose some 2 to form 1. And if mu1 is equal to mu2, then you know you're in equilibrium. Right? And then you go read off the amount of moles you have of N1 and N2, and then you'll know how much material you have. Right? That's your equilibrium constant. So chemical potential tells us something about how the system is approaching equilibrium. So, right, so one way you can think about this is that chemical potential of a material is the change in the Gibbs energy with respect to that mole number at constant temperature, pressure, and other components that aren't that one. Right, so it tells you, right, chemical potential tells you how the Gibbs energy is changing as you just convert, say, molecule 1 into molecule 2. It's a slope. But if you notice, this has the units, right? This just has units of Gibbs energy, which is kilojoules, per unit mole. And all this is, it turns out, is that this, in fact, is that mu sub I. Let me see if, should we come back to this in a second? Are we ready to do this yet? We're not ready to do this yet. Okay. I'm going to erase this yellow part right here. We're not quite ready to get this part. But it's still kilojoules per mole, right? So this has some sort of energy content in it. Okay, so let's do a little bit of math and see where it leads us. Okay, so let's assume a reaction. All right, in this reaction, we're just going to keep it as general as possible. I think I call it A plus B goes to C plus D. Let me just double check. I do. All right. So we have, let's start with A. So molecule A. Let's assume everything's in a gas phase right now. And I'm going to make some spaces because I gotta fill something in a second. All right. So let's assume gases for now. Liquids and solids are a little complicated. We'll come back to them later. Gases, of course, are easier. And we're going to say that this is an equilibrium with two other components, C and D. All right, but as we've aptly noted already today, that the ratio of these may not be 1-to-1, right? They have stoichiometric coefficients, right? So let's include the stoichiometric coefficients. And the symbol I like to use for stoichiometric coefficients is the Greek letter mu, or nu, which is like a V with little squiggles. We'll call that mu A, mu B, mu C, and mu D. Right? So these are the stoichiometric coefficients. Right, we have to always make sure that we keep our things in stoichiometric ratio. All right, so what we're going to do is we're going to take a look at this reaction. Right, we're going to put A and B in there in our box. We're going to let it equilibrate for a little while, react. It may be at equilibrium. It may not be at equilibrium. Okay, so let's say we're going to be in some system. So let's define, all right, so let's just say we're somewhere along the reaction path. Yeah, go ahead.
So you said before, right, that like at equilibrium, though your change in the Gibbs energy is 0.
Yes.
Is that true? So
yes, that's correct.
The coefficient's 0 at equilibrium?
The coefficients are 0 at equilibrium.
Not coefficients, I mean the chemical equilibrium. Like the...
Yes, that's correct.
Okay.
We'll see that in just a second. So assume we're along the reaction path somewhere. All right, so it's such that the reaction may be done, it may not be done, we're not sure. And so let's define the number of moles for each of our components. So imagine we have moles of A and moles of B. All right, so how do we define these? Well, first we'll define them relative to their starting materials, right? So this is the starting material. So imagine we put in 1 mole of A at the beginning. Right, and we have NB sub 0. These are, again, are the initial conditions, the initial concentrations, or the initial mole. Sorry, I'm having a, there it goes. I'm having a little bit of lag on my screen right now. Let me just close out of a few things on my computer. Ooh, it's taking a dump. Okay. All right, and we know that the system has moved along the path a little bit, right? So it's reacted a little bit. So we've lost a little bit of A and a little bit of B. Okay. So how much, so we want to basically, let's track this reaction kind of like on a click, all right? Like it's on a metronome, all right? Where basically A and B react kind of click, 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 right? We count them. Right, so it's not continuous. But, well, maybe it can be continuous, but just kind of think that it's kind of reacting kind of on a metronome. Okay? And so that means that if we measure the number of clicks, I can tell you exactly how many moles we have left. Right? Because I know every click, I'm going to lose new A of moles of A. So 1 click, if new A is 1, click happens, I lose a mole. Click happens again, I lose another mole. And so on and so forth. Right, so that means that the loss is going to be proportional to the stoichiometric coefficient. Times the number of clicks. Right, and I'm going to call that number of clicks N tilde. where n tilde is called the extent of reaction. All right, it's just a number. All right, if the system is continuous, then the clicks are continuous. But imagine it was just a metronome, right? It's just a number of clicks. Right? And every time, right, what happens? Every time it clicks, we lose mu A mole equivalents of A, mu B mole equivalents of B, and we, of course, gain that in C and D. All right, so I can go ahead and write NC is NC comma 0 plus the stoichiometric coefficient times n tilde and ND 0 plus the stoichiometric coefficient D, so D times n tilde. Right. Makes good sense, right? When the click happens, we lose some moles and we gain some moles. All right. Again, we don't know where we are in equilibrium, right? We could click one time, and we've somehow gone past equilibrium, right? We've created too many products. Eventually, the system's going to click backwards and go back to a different balance. Right? So there's going to be this balance between A, B, and C, D. Right? That's going to happen as a function of the clicks. Okay. So now we can take this idea, right? And so now what we can do is now plug these values into our chemical potential equation, right? So we have that dG is equal to the sum over all the components of their chemical potentials times the change in their moles. Okay, so now plugging in our click equations for each of these. Well, before we do that, we can write this now as minus, and of course this is equal to 0. No, let's not say that. We're not at equilibrium necessarily, sorry guys. So this is equal to mu, right? And remember the process of this reaction is every time we click, we lose A and we lose B, so I'm going to put a negative sign in front of them, right? Every time we click, the energy changes, and that means that A and B are disappearing and C and D are forming perhaps. So we've got to have opposite signs for A, B, and C, D. Right? We lose A and B, there'd be minus potential. We're going to get a gain of potential along C, D, or vice versa. So they have to have flip signs. So we have mu A, bless you, times the chemical potential of A. And then we have the derivative of the number of moles of A. So what's the derivative of this equation? So we're taking the derivative of N. So this goes away, it's a constant. We already have, and so what we're left with is just that the change in N is equal to the change in the clicks. Right? dNC is only proportional to dN click, because these are constants, right? So dNI is actually just, turns out to be d click. Like that. Right? And we can do that for all the components. Right? And then we get plus signs for the other ones. And again, I can change my sign convention, right? As long as they're opposite each other, right? Because you lose two and you gain the other. So as long as they're consistent, it doesn't matter. You get the same result, as we'll see. So it's just totally arbitrary. It seems to make sense that we think about the reaction when we start it, which means we're losing A and B to form C and D. And we're left with VD, UD, DN, click. Okay, so what I can do is I can divide the whole thing by dn. Right? So I now have that dg dn. Right? This is how the Gibbs energy of the system changes every click. Is going to be equal to, I'll just write it quickly, Vd mu d plus Vc mu c minus nu a mu a minus mu b Vb mu b. Right? So what this says is that as the reaction clicks, or progressing along, the Gibbs energy of the system is going to change proportional to the difference of the chemical potentials. Right? So if the chemical potentials of D and C are bigger, right? Imagine this sum right here is bigger than this sum. So maybe a better way to write this, for instance, is to say minus the sum. Maybe it would be different to write it like that instead. Right, so imagine this is bigger than this. Right? So that means every time the system clicks, which means you make A and B into C and D, and if this is bigger, then that means the energy is going to go up. Right? So that means we're too far. Right? We want the energy to go down. Right? So if we find that the chemical potentials of the products are larger than the chemical potentials of the reactants, then that means every time the reaction clicks forward, the energy is increasing, which means we've gone too far. So if this number is negative, however, if mu a, mu b times the coefficients is bigger than this, every time it clicks, the energy goes down, right, because the slope is negative, and that means we're approaching equilibrium. We're not leaving it. Right? So that what this means is that, again, that the direction of reaction depends roughly equal to the difference in the chemical potentials between the products and the reactants. We want this to be, right, in order to approach equilibrium, we want the slope of Gibbs to be negative, right? We want to go lower in energy as much as possible. Right? So that would mean that every click we need to lose A and B to make C and D. And if we've gone too far, the energy goes up because every click we make more C and D, and this term is greater than this one, and the energy increases. Okay, so equilibrium has something about the balance of these two things. Right? The chemical potentials of the products minus the chemical potentials of the reactants. Right? Again, this looks just like Gibbs energy or enthalpy differences, right? This is just like calculating the change in the Gibbs energy of the reaction is the Gibbs energy of the products minus the Gibbs energies of the reactants, or the enthalpies of the products minus the enthalpies of the reactants times their stoichiometric coefficients. They're all state functions. They all measure the same things just from different perspectives. Right? It's just another type of energy. Right? And this energy, the chemical potential, is this type of energy that tells you something about how the system is distributed amongst its different components. Right? It's the chemical energy of the system. So the idea is that mu is the chemical energy, chemical internal energy of the molecules. It has nothing to do with the box. Right? It has nothing to do with the box. Right? It has nothing to do with the entropy or the volume, none of the work. Right? This is some sort of internal energy that's intrinsic to each of the molecules. Right? And as you remove one molecule at some energy and make another one at a different energy, that changes the Gibbs free energy, which is the sum of all of the molecules' energies. Okay, so it's about a balance of stability, if you will. If you have a lot of unstable molecules, they're going to react as much as they can to form more stable ones. Right? The chemical potential tells you something about that stability, like a relative balance. How much time do I got left? Great, 10 minutes. All right, so I want to do one more definition, and then we'll see how this all comes together. All right, so what I want to do now is I want to see how to argue this. So what I want to do is I want to relate chemical potential to something I can measure. All right, because you might imagine you have a mixture of molecules that are reacting. In order to measure the chemical potentials, you need to ask each molecule, hey, what's your energy? Well, it's not very easy to do. All right, so we need to relate chemical potential to something that we can measure about each of the molecules, right? To make a kind of an indirect measurement, if you will. Chemical potential is not easy to measure. It's hard to measure energies in general, especially if things in a mixture. So we want to measure it to something that we can measure. All right? So remember, we're working with gases here. And each gas has its own partial pressure. Right? Partial pressure is the idea is that the total pressure of your system, of a bunch of gases, is a sum over components of all the little partial pressures. Right? So imagine, for instance, in air. This is an example. 1 atmosphere of air. Right? What's the partial pressure of nitrogen? Well, nitrogen has a, let's look it up. Does anyone happen to know how much nitrogen there is in the off the top of their head? I didn't think so. I don't either. 78. So N2 is 78%. Right? So its partial pressure of N2 is 0.78 atmospheres, right? Right, super easy. Right? It's just the amount of pressure it contributes to the total gas. Okay, so it's really easy to measure partial pressures. Right? Really easy. Just need a couple of separation technique and some pressure meters. Pretty easy to measure that. Right? So I'm not going to go through the derivation of this equation. It's actually really easy to derive, so it's not really worth talking about here. But we'll see this behavior a lot in this class. And so now imagine we want to measure the chemical potential of a material at some pressure in our component, right? It's not going to be necessarily standard, but we can relate it to the standard chemical potential. So we have the standard chemical potential. At STP. Right? And we will show eventually that mu I is equal to the Gibbs energy of formation of that material. Right, so that's the formation Gibbs energy. Like that. And it deviates, so at a different pressure than STP, because of course we might have a system that has a very small amount of material. It's going to have a different chemical potential. Ends up being RT ln, the pressure of that component, divided by the standard pressure. Right, so the chemical potential of a material, depending on its partial pressure, which is something to do with concentration, mole numbers, right? They're all related to each other, right? The more moles you have of a gas, the larger its partial pressure is, because you have a larger fraction of it. But the chemical potential varies as the log of it. Okay, so what's going to happen when we react A and B and C and D right, the partial pressures are going to change, right? You form A goes away, you form some C, partial pressure of C is going to increase, partial pressure of A is going to decrease, and that means their chemical potentials at each point along the reaction are going to change, and they change, at least to ideal gas approximation, to the log of that partial pressure. Right, this assumes ideality. Okay, so what I can do now is I can plug this equation into my expression for the Gibbs energy as a function of the chemical potentials. Right, so what I can do is take this equation and write that delta G at some point along the reaction is the stoichiometric, I'm just going to skip through some of the algebra here. Stoichiometric coefficient sorry, I'm using different labels. You probably wonder what the hell Y is. Of C times the standard chemical potential for C plus the stoichiometric coefficient for D times the standard chemical potential for D minus the mu A standard minus mu B standard. And then we have these logs, which are proportional to the stoichiometric coefficients. So we have the log of the partial pressure of component C plus the same for D minus that for A minus that for B. Or sorry, did I screw something up? No, that's right. For B.
Should there be two parentheses before the RT? Or after the RT? Because it's RT times all of that? Or?
It's RT times all of that.
Okay, so.
Yeah, I got it right. All right, so, but we can simplify this, right? Because we have a log times a number, so we can put this in as the exponent. Right, so VC log PC would be log of PC to the VC power. And then we have a difference of logs. Right, so we have, remember that the sum of logs is the product of the arguments, and the difference is the quotient. Right? It's the opposite of the log rules you've been using. So we can combine all of these terms together. But what is this number right here? Well, this is the stoichiometric coefficient, right? So let me just break this down. So we have this term right here. Remember that I said that each of the pure chemical potentials is just the Gibbs energy of formation, the things that you calculate from NIST. This is just the Gibbs energies of the products minus the Gibbs energies of the reactants. Right? So this is delta G of the reaction. Right? So this right here is delta G of the reaction at standard conditions. Right? It's what you calculate from NIST. Right? Right? And then, so we have this nasty RT thing down here. Right? So if what you can find now is it says now that delta G much time do I have? Okay, almost there. Is the reaction Gibbs energy plus, I'm putting all the terms together, RT times the log of PC to the VC, PD to the VD power, PA to the VA power, and PB to the VB power. And there's a additional, and so here we're assuming that P circle is 1 bar, so it just goes away. Right? And this thing, this quotient right here is what's called Q the reaction quotient all right, just one more line. All right, so it says that the Gibbs energy at any point along the reaction is the Gibbs energy of the reaction plus RT times the log of this quotient here, which is something to do with the partial pressures or the concentrations raised to their stoichiometric powers. Right? So let's assume the system's at equilibrium. One last line. So if delta G is equal to 0, so we're at equilibrium, then delta G reaction is minus RT ln Q. And in this situation, we call Q KEQ, the equilibrium coefficient. All right? So what the equilibrium coefficient is right, so all chemical potential is just splitting up the energy of each component of the reaction into the standard part, right, the reaction Gibbs energy, and then something that has to do with the imbalance of products and reactants. Right? So if you have an imbalance of products over reactants, for instance, right, delta G is not going to be 0 because this thing is going to be non-zero. And then if you're at equilibrium, delta G is 0, and these are equal to each other, and you get the equation. Right? I'll just kind of put it right here. Sorry this is so messy. You get delta G is minus RT ln K. Does anyone recognize this from Gen Chem? Right? So the equilibrium constant tells you the relative ratio of the concentrations of the pressures. Right? Well, eventually we'll be able to relate this to concentration. Chemical potential tells you something about the balance of the products and the reactants and their inherent energy differences. And the equilibrium constant is that number when the system's at equilibrium. Okay, so K tells us something about the relative ratio of the chemical potentials of the products and the reactants. All right? All right, so here we are, Gen Chem classic, right? So we'll come back to this equation and start looking at equilibrium at different points along the reaction and do kind of equilibrium from the first principles. And we'll see get the same results as Gen Chem.
But I thought that delta G is 0 when you're in equilibrium.
Ah, so good question. This is
really
different than this. Delta reaction of G, which is H minus Ts of the reaction, that's the heat and the work part. But delta G also includes the chemical potential part. So this can be non-zero.
Delta of the reaction.
The value of this tells you something about the relative ratio of the chemical potentials.
Oh, so the delta G, that's the G of the reaction.
This is the G of the reaction at equilibrium.
And that's what that...
This is what delta G is at any point.
Oh, so the delta G at any... Wait, but I thought the K was only at equilibrium.
Yes.
So wait, I'm confused. The delta G equals negative RT ln K is which delta G?
Oh, sorry.
No, it's okay.
Yeah, you're right. I'm sorry. There we go. Of the reaction at equilibrium. Right, but the point is that we can measure delta G at any point. And that's a sum of the inherent delta G of the reaction plus some energy asymmetry due to the fact that we're not at equilibrium in chemicals.
So when...
So this is the total delta G of the system.
And that's 0 at equilibrium.
And that's 0 at equilibrium.
Okay.
Right, exactly. Now, if delta G of reaction is 0, then that means the ratio of A to B and C to D is equal. Right, because it doesn't have any preference one way or the other. But the idea is that, for instance, this might tell you that the system's product favored. But you might be at a system where you have a lot of reactants, so delta G is not going to be 0 there, it's going to be positive.
Okay.
So what that means is that these have to change in order to make this to go to 0.
Yeah.
Does that make sense? We'll look at that more carefully tomorrow,
No, that makes
or
sense.
on Monday.
I feel like I asked so many questions today. I'm sorry.
No, I'm happy you did. I'm sure you're not the only person to wonder these things.
The negative RTL is negative. It's like, this is negative.
No, it's a positive because if this is 0, then you have this plus this is equal to 0. So one of them's going to go on the other side of the negative.
That was not my
We'll do an example of this next class, a direct example. And you'll see what I mean.
I didn't think we were going to be doing this, like, same thing like from quant.
Do you do this in quant too? Oh yeah, but you do. You do activities, don't you?
Yeah,
Well,
we do a lot of
but
that.
only about 4 of you have ever taken that class.
Yeah.
Yeah.
Us and
Yeah, exactly. So this is new to a lot of people.
Quant's a good class, though.
Yeah, no, literally. I was like, oh, this is just quant.
No, it's just I know it's a review for the quant
Well,
kids.
no, this isn't.
It's
Yeah,
not review, but it's
The K stuff, though, we're more friendly
Thank
than
you.
most.
yes.
Well,
And, like, it's not review, but it's familiar. Like, I'm
More
making
familiar
connections.
for sure, yeah.
So I just want to say, Monica, I will spend, and this is a linchpin for a lot of kids, the difference between delta G for your system at a given point and the delta G of the reaction.
I think it makes sense now that you said that.
So I'm going to separate, I'm going to make it very clear in our examples next class that there's a distinct difference between these two ideas.
Okay. Thank you.
I said you get 1.5 of change.
He emailed me.
Yeah,
I already submitted it. I'm leaving it.